Hello and welcome to our new video on how to learn tensor calculus. Well, in this video you will understand what tensors really are and why they are not just mere matrices, the common challenges a learner faces, and how to approach the subject step by step by selecting the right book and the right method. My name is Shaunak and you are watching this video on my channel Physics for Students. Now, before we go ahead in understanding what are the methods, books, etc., first let us understand that what is actually a tensor. And for that, I would consider this person who is just cycling. And here you can see that the direction of the cycle is along the x-axis. That means the bicycle goes straight to the right. Now, here we can describe the bicycle's motion simply as moving along the x-axis. That means the motion is to the right, nothing upward or in any other direction. So, by mathematics, we can represent this as 1, 0. So, it means that you are just moving one unit to the right and nothing upward. Now, consider the same person who is bicycling in this direction. So, the arrow points towards this. And here we can say 1, 1. That means some to the right and some towards the upward. So we describe this by saying that the motion has an eastward part as well as a northward part. And when we take the length of this kind of a direction, we get is this one and the square root of 2, which we can say as normalized northeast vector is around this part. So what is important to know is that whether it is going along the x-axis or you're moving some to the right or some to the upward, the bicycle's motion is still the same. It doesn't really care about the coordinate system, whether you're rotating or twisting or you're changing, and they give us a language that remains true. So what is that language? That is what tensors is, no matter how we set up the coordinates. So from here what we can say that the numbers change but the motion actually remains the same, and technically we call as something invariant. So from here what we can say mathematically is that if we take a flat surface and we move a vector A along this axis and we draw the components of the vector as AY and AX, we can denote the components by these blue dotted lines. On the other hand, if we take a curved space or a curved space-time, the axis goes around this. And if we plot the same vector A with its components, we will see that some of the components, say for example A prime x will be in this direction and A prime y. We can join the components and we can see that A prime x obviously is longer than the flat surface and A prime y is also longer. So that means that A is actually invariant. The vector actually remains the same and the red dotted lines or the red lines have changed, they have become longer. In a similar fashion, if I rotate this same axis, as you can see here, if I rotate it, then also we find that here the A prime or the AX or the AY denotes this, and we can see that the A prime X is a little bit longer, however A prime Y has become a little bit shorter. So this is the static frame of reference on the left hand side, this is the rotated frame of reference, and you can see that the components of the vector starts changing, however the vector remains the same. This is in a way the basic idea of what tensor is all about. So from here we can say that tensors are vectors which have not a single direction but rather pointing at different parts. As you can see, this picture illustration tells tensors have both the properties of vectors and a scalar. Tensor is not a scalar, we will soon see, because it is just an abstract quantity that obeys certain transformation laws. They are geometrical object that describes the linear relationship between geometrical, numerical and other tensile type vectors. From here what we can deduce is that we can say that tensor is a mathematical object. Remember, it is just a mathematical object which describes a kind of a multilinear relationship between sets of algebraic objects to a vector space. Now, in order to make this definition a little bit more clearer, we move on the next part of our video where we will try to show you that why tensor is not a matrix, because most of the students from linear algebra, when you move into tensor, you have a general notion that yes, tensors are basically matrices which are extended, but that is not. In order to illustrate that, you need to understand that if we take a unit square, or you all understand what is the unit square, we can denote this one and extend the direction of x by 2 units and the direction of y by 3 units. So on a kind of a matrix notation, we can write something like this, obviously. Now, when we extend the x by 2 and y by 3, it looks something like this. So the square actually becomes a rectangle of a size 2 upon 3. So 1 comma 0 is 2 comma 0, x is doubled, and 0 comma 1 is 0 comma 3, y is tripled. So what is important is that the key idea, you see that the transformation itself, stretch in x by 2 and y by 1, did not change, only its metric representation changed. That means the basic shape of the square still remains the same. So if we rotate, we will soon see that how we rotate the axis and we reapply the same matrix, the transformation looks different. So this shows actually a matrix is a transform vectors and shapes by scaling, rotating, or shearing them. If we could have shown a shear, that would have been better. But anyway, what it shows is that the transformation itself stretched by x by 2, and it does not change the overall rectangle or the square shape. Now if I go to the next part and if I take the same rectangle, which is 2 by 3, and if I again rotate this one, as you can see I've rotated the axis, you can see if you do the calculation, which is a little bit longer, you take the and multiply the matrices, it will come something like this. So here also what is worth noting is that the rectangle has not changed. As you can see, the dotted black lines of the rectangle, the physical stretching is still the same, but because I have tilted the coordinate axis, the numbers in the matrix are no longer 2, 0, 0, 3, but 2.5, 0.5, and 0.5 and 2.5. So that is why, remember, the matrix is not a tensor. The tensor is basically the underlying rule that tells you how you stretch. So from here we can find that a tensor is not a matrix. A tensor is a linear rule that can be written as different matrices depending on whether we rotate, shear, or whatever we do. So from here we can always tell that matrix is the representation, depends on coordinates, and tensor is basically the transformation rule independent of the coordinates. Now from here what I can tell you is that there are two ways in which a tensor actually transforms. One is called a covariant tensor and another is a contravariant tensor. However, in this part of the video I will try to explain you what is a covariant tensor. I want you to imagine a space-time diagram or a simple diagram and a coordinate which has got t as time and x, y, z as a spatial coordinate. So contravariant vector actually changes in a specific way. How does it change? Let us consider this to be a space-time continuum, or you can consider that to be just a plane or a space. Now I have got a vector which is this one pointing in this direction, and in order to make the vector divide in components, I see there are two blue components, one green component and one red component. Now what I am going to do is that I am going to stretch this space-time and it will look something like this. So you can see it is sufficiently stretched. But I am considering the same arrow, the same black vector. Now what you can see because of the stretching, here you can see that we need only 1 unit of blue vector, 1 unit of green vector, and tentatively 1 unit of the red vector. The diagram I have drawn it manually without mapping the coordinates, so apologies, it might look a little bit different. So what we can see is that as you stretch the grid, the arrow stays the same physically, but the original coordinate system, the unit is 1 meter long. However, if you reach out the vector, you now need 3 sticks instead of 1, 2, 3, 4. So if I now measure the vector, it will be 3 units multiplied by 1 meter. So if you define the coordinate system where each stick is 2 meters long, I would just take 3 by 2, that is 1.5 units. So what do we get from here? We need now only 1.5 stretched sticks to get there rather than the 3 units multiplied by 1 meter. So from here you can see that the vector actually does not change. It still points at the same place. This is something very, very important, and this reflects the idea of a tensor. So here you can see simple, this has got 3 units, 1, 2 and 3, and this stick has got only 1.5, that is only 1.5 units. So inference can be drawn from this kind of an illustration, that what is happening is that you are measuring the physical quantity which are fewer in number. That means it has become less, which was more has now become less. So that is why the component, that means the how many sticks you need, shrinks when the basis grows, and this is why it is called contra, that means opposite. You stretch the basis and the number of arrows shrinks. So the vector itself is geometric, it doesn't care about the coordinate. The coordinate components adjust inversely in how the vector changes, and this is how we denote v to the subscript of I. When we are putting the indices on the top, that means it is a covariant vector. When we are putting it at the below, it means contravariant vector. So this is how a vector actually, or the tensor actually changes, and the vectors points the same direction, the basis grows, the number of components actually shrinks. In a similar way, there is something which is a contravariant vector, which I have not shown because it is more on the methods and books review that I am going to talk about in this video. So if you want to know more, I would say go to my playlist on tensor calculus on my channel Physics for Students. There is a live video and there are other videos where you can find out more on these coordinate changes, the concepts, the history, and few things more. So having said that, we now move on the next part of our understanding, that do tensors have application beyond physics and mathematics? And the answer is a very big yes, and this actually opens up areas where you can now go in terms of further researches. The first thing that we get is engineering, and here you can see that structural engineering, stress and strain of the materials are second rank tensors. Fluid dynamics, viscosity tensor describes how fluids resist deformation, and continuum mechanics, general framework of how solids and fluids deform. You can also find a lot of applications in computer, because transformations are tensor operations used in rendering 3D scenes, simulating lighting and animation objects. Robotics, yes, used for tensor-based kinematics for describing orientation and deformation. Biology, modeling, biomechanics, protein structure analysis is being used. Medical imaging, diffusion tensor, which is called diffusion tensor imaging, DTI, models how water molecules diffuse in tissues. It helps to visualize nerve fibers and brain successfully. Geology and earth sciences also uses tensors. Artificial intelligence, NLP, I would say, use tensor embeddings to capture semantic relationships between words and sentences. Chemistry and material science also uses a lot in terms of tensors, and data science, which uses deep learning, especially frameworks like TensorFlow and PyTorch, literally treat all data as tensors. So if you are venturing to learn tensors, understand that it is not only restricted to physics and mathematics, but in various other areas of science. We come to the first book, which is a kind of a Bible, and this is a very simple book to learn, which is called Daniel Fleisch, A Student's Guide to Vector and Tensor Analysis. Now this is the cover of the book, and the Amazon rating, I won't wonder if the 5-star goes beyond 90%. This is the photograph of Professor Daniel Fleisch. Now as we see, this book is actually starting from vectors. So if you are not a person who already know tensors, or if you're thinking that, well, how will tensors behave, and it is a very difficult thing to do, you can very well start with the book as the content reflects. It starts with vectors, operations, Laplacian, vector applications. Then you will see it will contain covariant and contravariant vectors, which I just examined, the higher rank tensors, the tensor application, the metric tensor of general relativity, and a lot of interesting stuffs. So yes, this book is very much used in plain language, ideal for any beginners. It is very accessible, coherent applications. It starts with solid foundation in vector calculus and then proceeds, and the later chapters on tensor calculus are relatively brief. Deeper topics like Riemannian geometry and manifolds have been omitted for certain reasons, but the book is good enough to understand tensor calculus. We move to the next part of our video where we are going to look in another very famous book which is called Vector and Tensor Analysis by G.E. Hay. This is again the cover of the book, and the Amazon rating is a little bit low, 68%. So if you look in the content of the book, it starts again building the basics. So that is really wonderful. It will start with the operations, integration with respect to scalar variables. Then it comes to applications of geometry, area of triangle, and so on. It will further go in building your base in applications of vector to mechanics, which is the kinematics, the motion of the rigid body, and then it will move to partial differentiation. Here you can see I have highlighted in red box. This is where the differential geometry part is also being taken care. As you can see, chapter 3 will be on applications, integration, and chapter 6 onwards we will take care of tensor analysis. So a very good book which has been taken care of every part of vector analysis. It is a little bit older because it is a 20th century, and the tone and traditional is not that informal like Fleisch. And the strengths are, it is very rigorous in terms of mathematics, wide range of examples. If you are engineering students trying to understand the bridge between mathematics and applications, it is great. Yes, it has got limitations because it is a little bit old fashioned and not ideal for complete beginners because it directly jumps in the mathematics. Next, we look in another great book, which is this one, Borisenko and Tarapov's book on vector applications. Again, as you can see, the Amazon rating is around 74%. The content of the book, again, all these books are actually building you from the base, so you can pick up any one of them. Vector algebra, it goes into products of two vectors, then comes the tensor concept, the zeroth rank order tensors, then into the higher orders, coordinate curves, tensors in generalized coordinate system, and so on. Further, you can see this book is got, I have shown this customer review. So this is basically where the tensor algebra and tensor analysis takes place. And then you can see the ramifications are also being taken care, differential operators, integral theorems, and so on. Not a very dense book, 240 pages, but it is good for a basic understanding. It contains a lot of beautiful diagrams, as you can see, to make you understand about the visualization part. I would say that it is a little bit, this is also Soviet tradition book, so it has emphasis on the mathematical rigor. It has got good strengths because it covers all the essential machinery you would require, particularly good in continuum mechanics, and also this is a good bridge from vector analysis to tensor analysis. The next book is particular to physics, and for those who are learning tensor calculus for physics, this book would be useful. It is called Tensor Calculus by Dwight E. Neuenschwander, and this is the photograph of the great author. The 5-star rating goes up to 78%. The content of the book, why tensors are needed, again it is more on the context of physics. So what is the theory of relativity, then the two index tensors goes on and so on. And here you can see the electromagnetic stress tensor, the relative motion. So it is all related to mostly relativity and in terms of physics. So it goes further into signs of the trouble, affine connection, and finally ends. Not a very dense book, but it's a good one for learning the physics part and how it relates. Here you can see Riemann tensor, curvature, covariant electrodynamics, all these are dealt in. So overall, I can say that it also contains tensors and manifolds, and then it goes into exterior products and differential forms. So yes, it is a good book for graduate physics, especially keeping physics in part, written with the struggles of physics students in mind. Good to clarify this misconception that tensor is not a matrix, and it goes in general relativity and further. The next book would be a little bit more mathematical, but very good book. This is the cover, Prasun Kumar Naik's Tensor Calculus and Differential Geometry. It is going up to 69% of the 5-star rating. As you can see, it starts directly with tensor algebra, so don't think that this book will give you a very intuitive understanding, but directly in the mathematics. So you can see it jumps directly from chapter 2 to Riemannian metric, then goes into Christoffel symbols, covariant differentiations, Riemannian geometry, and so on. So the Einstein space, the intrinsic geometry of surface, curves on surfaces, relativistic mechanics, everything has been covered in details. So the style is little bit rigorous, obviously, because we are learning mathematics. Strengths, comprehensive, rigorous, includes a lot of examples. And who should use it? This is very suitable for graduate level mathematics students or advanced graduate students, or for those who are learning tensors in a very mathematically rigorous manner. So we come to the summary of today's video. We talked a lot about what is a tensor, why tensor is not a matrix, how a tensor changes using a covariant and a contravariant example. We have also looked into a lot of books, around 5 books which we have seen, and you can pick up any one of those books starting with Daniel Fleisch and go on. However, there are a lot of videos which I have made on my playlist, Vectors and Tensors, on this channel, Physics for Students, where you're watching this video, and you can pick up and watch these videos. These are good, intuitive, mathematical, short videos, long videos, related to general relativity, some other more resources and so on. This would give you a fairly good idea on how to learn tensors. Well, that's all for today's video. Thank you very much for taking your time and watching this video. If you have liked, please do not forget to subscribe to my channel Physics for Students and keep the bell icon so that you get all the notification from this channel. You can follow me on my Facebook handles, which are quite active nowadays, and you can write me to this email ID. That's all for today's video. We'll see you soon in another interesting video, but till then, may the good Lord be with you.